Okay, we're going to be looking at an alternative method of working out problems where three forces are acting on an object in equilibrium. And that is the triangle of forces and Lami's theorem. Now, technically, Lami's theorem is not part of the syllabus. However, it provides a nice way of working out some of these problems. If you think about when you've got a situation where you've got three forces acting on an object in equilibrium, those forces are vectors and you can draw them so that they have no resultant because there's no unbalanced force acting on the object. So we can basically set up a triangle of the forces and use the results of trigonometry to work out what we're trying to discover. So let's see what that actually means in practice. So what we're looking at is by drawing a triangle of forces, we can use the sine and cosine rules directly without resolving components. The lengths of the sides will be the magnitudes of the forces. So let's just quickly remind ourselves of the sine and cosine rules. So we've got A, B and C, and this is length, little a, little b and little c. So our sine rule is little a over sine A equals little b over sine B equals little c over sine C, and for the cosine rule it is a squared equals b squared plus c squared minus 2bc sine A. So I'm just going to leave those here. So let's think of the kind of situation that we've got. We have some particle and there's these forces acting on it. Force A, force B, and force, I would change that because it looks like looks like they're perpendicular but they're not. Force C is. Now what we can do is we can redraw these in as a triangle. So let's redraw our vector for C. Okay, now if we take vector B and we just move it along their parallel, we will bring it to here. And then if we were to take vector A, and say we moved A along the B vector till the end of A came to the end of B, it would be coming here and it would join up with C here. So there we've got a nice triangle of our forces. Now, let's take this a wee bit further. The end of vector A, where the vectors B and C meet, we're going to call this alpha, and we're going to call this angle at the end of where A and C meet beta, and we're going to call this angle where B and A meet gamma. Now let's look at where those then appear in our triangle. So when we move vector A along to where it is here, if we were to draw a dotted line coming out of the end of here, we would have this as gamma, and likewise this would be alpha, and this here would be beta. So if we apply the sine rule to the triangles, we would have A equals sine, and at this angle here is going to be alpha 180 minus alpha. So sine 180 minus alpha is going to equal to B, vector B, which is this one here, is going to be over sine 180 minus beta equal to C, sine 180 minus gamma. And since sine theta equals sine 180 minus theta, this leads to the following: A over sine alpha equals B over sine beta equals to C over sine gamma. And then we get, this gives us Lami's theorem. So Lami's theorem states that for a particle in equilibrium, with three forces on it, the ratio of the magnitude of the forces with the sine of the angle between the other two forces is the same for each force, which is what we have here. Okay, so let's look at an example to see how this works in practice. So we've got an object in equilibrium. I'm just going to write equilibrium, we can write that, by the action of the forces 10 newtons, 8 newtons and 9 newtons. And it's shown like this. So we've got our 10 newtons, and then we've got 8 newtons, and we've got 9 newtons, and they're an angle theta and phi. So we want to find the angles. So we're going to redraw this as a diagram of forces. So we'll keep the 10 newtons where it is. And just up. Now we're going to take this 8 Newton force and we're going to slide it along till it meets the tip of the 10 Newtons. So we'll end up with it here. Now what happens to this angle theta? So if we are moving it up here, each time we move it up it's always in parallel. Let's just extend a wee dotted line at the end of our 10 Newtons. So that means this angle here will be theta. Now for the 9 Newtons, let's slide the 9 Newtons so it comes to the end of where the 8 Newtons are. So if we were to bring it along here, at the end of the 8 Newtons we'd have this angle, this vector for the 9 Newtons. It would come down here and it's going to meet the beginning point of our 10 Newtons. Now what happens to our angle phi? So the phi angle is going to end up, we end up extending our 10 Newtons down here. This is going to be phi Newtons. So we can now use our cosine rule. So the cosine rule, as previously stated, was a squared equals b squared plus c squared minus 2bc cosine a. So let's think about it first for here, for this angle here. So we would have, for this, we would have opposite here is going to be 9 squared is equal to 10 squared plus 8 squared minus 2 times 10 times 8 cosine. Now this angle in here is going to be 180 minus theta. And if we work all that out, we'll get cosine 180 minus theta is going to be 8 squared plus 10 squared minus 9 squared all over 2 times 8 times 10, and theta will be 121.2 degrees. Now we can do the same for the angle down here, and if we use the cosine rule again, we will have 8 squared this time is going to be equal to 10 squared plus 9 squared minus 2 times 10 times 9, and it will be again cosine, this time is 180 minus phi. And so we'll end up getting the angle for phi as, I won't do all the working because it just works out the same way, 130.5 degrees. Now, let's look at the problem of ship is held in equilibrium. By ropes on a bearing 120 degrees and 220 degrees. The wind blows due north with a force of 90 newtons on the ship. Find the tensions on the ropes. So first let's draw our force diagram. So we've got our boat here, and we know there is a force due north of 90 newtons. and we have the ropes on these two bearings. So we've got one bearing is 120 newtons, 120 degrees, sorry, and we're going to call this T1. And then our second rope is at a bearing of 120, so from the north we go round 100 and so round from here to here would be 210, but this is 120, so that'll be, this makes this angle here 100, because, we'll just quickly write it here, 120 minus 110 is obviously 100. And this will be tension T1. So we're just going to use Lami's theorem. We know that 90 over sine 100 must be equal to T1 over, well, what's this angle here? Well, this angle here must be 140, because 360 minus 120 minus 100 is 140. So this must be sine 140. Now if we just rearrange all that, we're going to get T1 is equal to 58.7 newtons. Similarly, 90 over sine 100 must be equal to T2 over sine 120, which will give us T2 is equal to 79.1 newtons. Let's look at another question which is going to be a bit more challenging. So we have a particle and it's in equilibrium, it's held in equilibrium by three forces. And this is shown in this diagram. So we've got our particle and it goes 40 newtons up here. Then we've got some force here, F. We don't know what that is, but it's at an angle of 120 degrees. And then we've got the third force down here, and that's at some angle alpha, and that's 50 newtons. We want to find F and alpha. Now, we need to be aware, for this to be held in equilibrium, alpha must be greater than 60 degrees. Why is that? So if we were to draw a line down here, so that's that is a straight line there, so it's going to be 180. 180 minus 120 is 60. So that angle must be greater than 60. Otherwise the particle won't be held in equilibrium. If it was less than 60, the force here, this force of 50 newtons, would be fell in to the right, so there'd be no force pulling on towards the left, and if all the forces were pointing to the right, the force would be moving. There'd be an unbalanced force. So we need, alpha has to be greater than 60. So if you were to, and this is important because if you were to do, say, just apply Lami, 40 over sine alpha equals 50 over sine 120, you're going to find alpha is 43.9, which mathematically is a solution, but in our problem it won't work. So what we're going to do is we're going to think about force F, and we're going to break it up into the components of the force acting on the particle perpendicular to force F. That means the F newtons is going to be cancelled out because there'll be no force acting perpendicular to force F. So let's do that. and hopefully it'll become clear as we look at it. So let's look firstly at what comes from the 40 newtons perpendicular to F. So here's F, okay, and we're going to extend F along a wee bit, and then we've got our 40 newtons, and this is perpendicular. We've got this 120, so this angle here must be 180 minus 120, which equals 60. So we can now find the force here perpendicular. So that must be, this is 40. So 40 sine 60 must be this angle. Now let's think about what comes from our 50 newtons. So again, we draw F, and we've got and extend it back. We've got our force here, that's alpha, and we have, this must be 180 minus alpha, and here's our, it's a little bit longer, here's our perpendicular, so this is 50. So sine 50 times sine 180 minus alpha, that's that angle, must be the perpendicular component of the force to F. And the perpendicular component from this force, the 40 newtons and the 50 newtons, must cancel each other out for the particle to be in equilibrium. So we have our 40 sine 60 must be equal to 50 sine 180 minus alpha. Now if we do that, we get alpha equal to 136.1 degrees, just rearranging that, which is 180 degrees more than 43. So it comes from that, the whole thing of sine, think sine theta equals sine 180 plus theta. So that's why mathematically that is a solution. But this is the one that works practically. Now, what we can then do with this is we can now use that in Lami's theorem to give us the force F. So F over sine of, now what, we need to think what this angle is going to be. It's going to be 360 minus 120 minus alpha, which is 136.1, must be equal to 250 over sine 120. Now if you work all that out, you will find that F is equal to 56.1. Now there's another method you can use. We can also use the triangular forces. I'm going to try and squeeze it in over here. So let's redraw the diagram as a triangle. So we'll keep our 40 newtons up here, and now we will move our F newtons along so it kind of comes out here. This is our F newtons, and we will move our 50 up. So it starts here and it comes down here. Now the tricky thing with this is making sure we understand what angles correspond to what angles on our triangle. So we moved our alpha up to here. So if we extend this out, this should still be alpha. And if we extend our F newtons down here, this will still be 120, because if you think about, we've basically just redrawn F newtons in this direction up here, but that's still, if we dot it down here, that's still 120. And then we can, let's just call this angle in here beta. So here we can use Lami to do 40 newtons, which is this, would be sine 180 minus alpha, which is equal to 50 sine 180 minus 120, because we want this angle in here. So that'd be end up in 60, and then we can, doing that would get alpha equals to 43.9 or 136.1, which is what we got here. And for the same reason, this is our solution. And we can then take that to work out the size of F. So I hope that helps.